not think of water as being magnetic, but it is, and so are graphite, aluminum, and glass. This is a new and different category of magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron, or nickel, or cobalt, becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet. And so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen which sticks to the magnet. I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet. Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnetic field. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end. Pyrolytic graphite is a grown crystal of flat carbon layers which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present when they're chilled. They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic fields. One way to check whether an object is diamagnetic or paramagnetic is to see how it aligns itself in a magnetic field. Diamagnetic objects like glass will rotate to avoid magnets. Here, we see that the glass is diamagnetic because it twists to get to the weaker magnetic field. But aluminum rotates into the field, typical of a parallel paramagnet. On the periodic table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamagnet? You have to know what the electrons are doing. Consider, for example, aluminum. We see from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p. Now it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that is free to be magnetized and attracted by the magnet. But what about a diamagnet, like water? Yes, the water molecule. It has all of its electrons paired. It will not be magnetized. In fact, water is repelled by a magnetic field. The electrons come to lower energy as they are moved away from the magnet. In conclusion, when something is a paramagnet or a diamagnet, it tells you what its electrons are doing. In the case of a paramagnet, it has at least 1 unpaired electron. In the case of a diamagnet, it has mostly paired electrons.
DiNardo here in the physics department of the Naval Postgraduate School in Monterey, California. When a charged particle moves through a magnetic field, a force on the particle can occur. This is the fundamental magnetic force. In this video, we will present a demonstration of the effect. In other videos, we will use the concept of the magnetic force to explain other demonstrations, including a jumping wire and a loudspeaker. This is a cathode ray tube, which produces a beam of electrons. The beam is visible due to argon gas in the tube. The electrons here are moving so fast that gravity is negligible. Watch what happens when I bring a magnet near the beam. The beam deflects, which shows that there is a transverse force due to the magnet on the moving electrons. In general, any charged particle that is moving in a magnetic field will experience this fundamental magnetic force.
So today I'm at the University of Sydney with Dr. Phil Dooley, and we're talking about how our idea of the atom changed from a tiny little hard sphere to something more complicated. And this apparatus has something to do with that.
Exactly. It was quite a landmark historical experiment. It's just made of a tube of glass connected to a vacuum pump. And in the tube of glass there are two pieces of metal connected to a high voltage power supply.
So we can suck the air out of here.
That's right.
And then apply high voltage to two metal plates.
Yes.
Okay.
Normally with high voltage in air we don't get anything except maybe a big spark. But what Geissler found, who did this in 1857, was something quite different. So shall we have a look?
Let's do it.
Okay, let's turn on the pump and the high volts. Turn off the lights so we can see what's going on. As you can see, something's happening now.
Yeah, I see a bit of a pink glow in there.
That's right. So imagine Geissler, the first person to ever see this. It's pretty surprising. That started people thinking, what is this stuff that's coming from the cathode? It seemed to be a ray emitted from this negatively charged one, which they called the cathodes, therefore it's called a cathode ray. And it became the topic for research for the next 40 years as all the big wigs of physics and science basically tried to work out what was going on.
So what did they figure out? I mean, what is going on? What's producing this, this glow here?
There were two main camps. One thought that it was waves, and the second thought that the electricity was being carried by a stream of charged particles. Over the next 40 years, they basically came to the conclusion, well, it was J.J. Thomson in 1897 who came up with the idea that there is a stream of very small charged particles, negatively charged. They're smaller than an atom. So the smallest atom, hydrogen atom, they're about 1,000th of the size of that. And it doesn't matter what material the metal is, it's always the same particle. So this particle appears to be in everything. Yeah, this electron, as it was known, is what's carrying the electricity.
So Thomson came to the conclusion that all atoms have this particle as one of their constituents.
That's right? That's right. So it wasn't a billiard ball, there had to be something inside the billiard ball.
Organizations designed you.